folks, and welcome to Lecture 2. So today's goal is going to be to introduce to you something called the wave function. And to get to this point of understanding the wave function, which is the central concept of really most of classical mechanics, there's going to be a few steps that we go through today to get there. To start off with, some of you, or all of you, have taken classical mechanics at Spelman College, but for some of us, it may be a little bit rusty. So we're going to start off with a brief review of some of the key concepts from classical mechanics that you'll need for this course. The second thing that we're going to do is we're going to introduce to you a new mathematical function called the wave function psi. And we're going to focus on two aspects of psi. One is going to be its mathematical properties. What can we know about this function mathematically? And two, what can we know about the function in terms of its physical or its chemical interpretation? And then last but not least, we are going to introduce the Schrodinger equation to you for the first time in its two different forms that you might see in the literature. One being its time-dependent form and another being its time-independent form. And this introduction to Schrodinger's equation, we're going to introduce during today's lecture, but really where we're going to dive deep into this equation is starting in Lecture 3. So with that, let's get going. All right, so classical mechanics, as you know and love it. I'll throw out to start off a brief caveat that everything that we do today, and really through maybe about Lecture 7, is going to be strictly in terms of one-dimensional systems. We'll treat 3D systems, but a lot of the math looks cleaner for a one-dimensional case. And so I'm going to start us off with our classical mechanics review, just focusing on a one-dimensional picture. And so some of the things that I hope that we remember or that is being refreshed right now for us in terms of classical mechanics is the different quantities that you might see in a course. One of those really important quantities is position. Position is denoted using the variable x. And sometimes if we want to talk about how the position of a particle that we're talking about in classical mechanics might change over time, we'll use these little parentheses and put a t inside to indicate that the position of a particle can change as a function of time. And I note this, even though maybe it comes across as somewhat obvious, because physicists and chemists in the textbooks that you'll see, sometimes we're lazy. Sometimes we'll write x when we're not focused so much on its time dependence. Sometimes we'll put the parentheses to talk about explicitly what are the independent variables in this case. And so one thing we're going to have to get used to in this course is recognizing that whether or not we list the arguments or the implicit, the independent variables for this function explicitly, it's still the same function. All right, so next up, we've got the velocity of a particle, and that is determined by taking the first derivative of the position with respect to time. Similarly, we can talk about the acceleration of a particle, and that is the second derivative of the position of the particle with respect to time. Now, it turns out that all of those variables, position, velocity, and acceleration, are sort of correlated with one another. They all reference something about the position of the particle as a function of time. So our second unique variable in classical mechanics, if you like, is the momentum. The momentum has the velocity as part of it, but we multiply it by the mass of the particle. And that is enough to make this a unique variable, such that if you go on in physics courses, you will hear people talk about being able to describe any state of a particle just as a function of its position and its momentum. And so that's also what we're going to do here. We're really going to focus on these two variables, x and p, as a way of describing everything that we need to know about the dynamics of a system as a function of time. Now, x and p, if you like, are sort of our independent variables that control the motion of the particle. Where is it? How is it moving? But what determines the position and the momentum of the particle? Well, it turns out it is the potential and kinetic energy that are associated with that particle. So kinetic energy is something that does not really depend, you can see that it just depends on the particle's momentum. So kinetic energy, you may have either learned the formula 1/2 mv squared in your physics course, or if we do a little substitution in terms of the relationship between P and V, you'll also notice that the kinetic energy is P squared over 2m. And in this class, I'm going to use the capital letter T to talk about kinetic energy. The potential energy, on the other hand, that is something that, well, it really depends on what circumstance the particle finds itself in. And so to provide you of a concrete example of one way of thinking about potential energy, an example you may have been given in your physics class would have been a mass on a spring. So here's the potential energy. This graphic that I pulled up is using PE, but we're going to use V of x in this class. And what we can do is we can graph the potential energy of a particle as a function of its position. And this potential is arising because, like the name implies, we've got some sort of mass here. I'm just going to make our particle like a little box with letter M. And it is attached to a spring. And then, of course, it doesn't really make sense unless the spring is attached to something else. So what I want you to imagine is that our position, and I'm actually going to redraw this slightly so that it lines up nicely with our axes. That as a function of x, if our particle is at the position x equals 0, which now I've tried to line up our graph and our little drawing. So this mass can move back and forwards as we pull or push on the spring. And as I've drawn it right now, the low part of this potential energy is sort of where the particle would like to be at equilibrium, to use a chemistry term, or in the absence of external forces, to use more of a physics term. So at equilibrium, we're at this low point for our potential energy. This is what would happen if you just had a spring and you left it alone. If we want to take this particle from its, so here's my wall, here's my particle. If I want to take the particle and either stretch it against the spring, or if I want to compress it closer to the wall, both of those things are going to raise the energy of the system. And that's because you have an external force acting on that object, either to push it closer than it really wants to be to the wall, or to pull it farther away from the wall that it really wants to be. And so what the chemistry connection that I want us to make for, taking what we learned in classical mechanics about potentials and turning it into our chemistry discussion for quantum chemistry is just to recognize that our systems, like all systems, are described by potential energy. And the way that potential energy translates to what the particle wants to do, or in chemistry terms, where we would expect equilibrium to lie, is for us to recognize that the total energy of a system is equal to the sum of its potential and its kinetic energy. And to make the connection to your Chem 345 class explicit, frequently, even though in this class we're going to use the capital letter E to describe this internal energy, in Chem 345, you frequently used U. To describe this energy. And so, just like we talked about when you were doing thermodynamics, for a system that doesn't have any external forces acting on it, and also I'll give a caveat, for a system where we don't really have to worry about entropy effects, which I will promise you we will not worry about until the very tail end of this course. So this mass on a spring, we don't really need to worry about entropy. So for a system like this, where the only thing that matters for its free energy is the internal energy, minimizing the internal energy means that we're dealing with, is going to make the system more stable or closer to equilibrium. And that's why I've drawn at the minimum of our potential energy curve our equilibrium position. So again, just to put that in writing, our chemistry connection is that in the absence of external forces, again, so it's not as if I'm pushing or pulling on the spring, I'm just leaving it be. In the absence of external forces, systems tend to minimize their potential energy. And it's possible to get the system to exist at a higher potential. Again, I can actively pull on the spring or push on it, but external effort is required in that case. We need some external energy input. Okay. And so that's really all that I want to say about classical mechanics at this time. The things that we're really going to focus on for this course is remembering our definitions of position and momentum and having a good intuition for both the kinetic energy, which is a function of the momentum of the particle that we're dealing with, as well as the potential energy, which is a statement about where the particle's lowest or most stable place to be is in the absence of external forces. Okay. So now that we've reviewed classical mechanics, we're ready to talk a little bit about quantum mechanics. And so there would be a whole lecture in and of itself of talking about the history of how it was that scientists in the early 1900s started to recognize that while classical mechanics worked really well for objects on the scale that our human eye can perceive, for really small systems, and by small, I mean roughly the size of an electron or a proton, but not as big as a protein. And also by small, I mean that you'll get an opportunity on the homework to explore just where this borderlands is between where classical mechanics works and where quantum mechanics works. But scientists realized that for very small systems, classical mechanics started to give wrong answers. And so much so that an entire new field of physics was required to describe the behavior of electrons and atoms. And the reason that we want to talk about classical mechanics as chemists is that electrons and atoms is exactly the world that we live in. And most interesting chemistry comes down to why it is that electrons behave differently than baseballs. And so I am going to introduce quantum mechanics to us by making a really big leap and giving you some of the central ideas of quantum mechanics as an axiom rather than trying to derive them. Quantum mechanics is unintuitive. Most of what we learn in our courses and what feels natural is ways in which what we observe in the world matches up with math that we see on paper. And unfortunately for quantum mechanics, it's not something we can see with our eyes. And so probably during parts of today's lecture, the axioms that I'm going to go through are going to seem non-intuitive. And that's okay. What I want you to do for today's lecture is to trust the math of what we're doing and to accept some of these axioms. And over time with practice, quantum mechanics will still probably feel strange. It still feels strange to me, but my hope is that you'll start to feel comfortable with the math that we need to do in order to get there. Okay, so here's the big, highly non-intuitive idea of quantum mechanics. Unlike classical mechanics, in this quantum world, we are not allowed to know the exact position of a particle. So if I'm an electron, I can't pinpoint it in space and say, here it is. This is where the electron is. The strongest statement I can make about the behavior of the electron is to talk about its probability. What I can talk about with something small like an electron is its probability of being in a certain location. And so now we can start to make a connection of why is it that I started off this course talking about probabilities and expectation values. It's because quantum mechanics is a world of probabilities and expectation values. And so mathematically, the probability of an electron or a particle, again, A particle can be very different things, but sometimes you'll see me slip into talking about it as synonymous with electron because in a chemistry world, electrons are frequently the most common particle that we talk about that has to be treated quantum mechanically. So our particle, which may or may not be an electron, but probably for practical purposes is going to be an electron. My mathematical notation here says that P of x, the probability that this particle is at position x, is related to something called the wave function squared. And so in terms of my notation here, notice that one, I'm using the capital Greek letter psi in order to discuss this. So here's my capital Greek letter psi. And psi, if I want to explicitly talk about what are its independent variables, it depends on x, the positions that the particle could be in, and t, the time that we're at. Because sometimes the wave function changes as a function of time. And most frequently, you'll see people use these absolute value signs and then squared. Frequently, the wave function is a complex function, and so it would be more appropriate for me to say that the probability is psi star, where the star means the complex conjugate of a function, times the wave function, the original wave function itself. And so if, as a way of a concrete example, if for some reason my wave function happened to be e to the 5 minus I, 5x minus I, let's say, then that would mean that P of x in this case would be psi star, which is going to be 5x plus I, that's our rules for what a complex conjugate means, times e to the 5x minus I. And that would be the function that defines our probability. I should make one quick correction here that technically this probability, if psi is dependent on time, maybe the probability varies as a function of time as well. Okay, so that's kind of the math of what this so-called Born interpretation is. And knowing that we can know something about the probability of the particle is useful to us. Unfortunately, I've really just brought up a new question, which is great. Now I know what the probability is in terms of psi, but I don't know what psi is. I have no intuitive grasp for what this means, and I have no mathematical grasp for what psi to be, what I should expect psi to be. And so now we have to talk, if we want to know the probability that a particle is going to be in a certain place, we have to talk about, well, what is the wave function? So let me give you two answers to that question, both of which are going to be, let's say, modestly satisfying, but something that we're going to have to keep unpacking as we continue on lecture-wise. So one answer I could give you would be a purely mathematical answer. The wave function is a function. And historically, the reason that it got called a wave function is frequently the wave function is made up of sines and cosines and other things that kind of squiggle around like a wave, hence wave function. If you like, they really should have called it the wavy function, but wave function sounds more professional. Okay, so it's just a function like any other that you've encountered in mathematics. And I'll give you a concrete example of one type of wave function that we'll encounter later in this course, just so you can see me play around with the math in a little bit. Psi, the wave function, has x and t as its two independent variables, but also, and something that you would not have seen from the Born interpretation equation that I gave above, is that psi changes depending on the potential that a particle is subject to. So in our example above, we had a particle that was attached to a spring, and it had a certain potential associated with it. Quantum mechanically, if our particle, that little box, was very, very small, that would mean that psi, we have to solve for psi knowing something about what v of x looks like. But if v of x changes, psi will also change. And that means that I can't give you a universal explicit mathematical expression for psi, like to say psi is equal to sine of x or equal to cosine of x. It changes depending on the situation. So I can give you some examples of types of psis that you might encounter, and we'll do one example in just a second, but unfortunately there is no universal explicit expression for psi. Nevertheless, we can put a few mathematical constraints on psi. The first constraint is something that's going to harken back to our first lecture. Constraint number 1 mathematically is that psi squared represents a probability. And therefore, in the same way that last time we talked about how if we have a set of situations and that encompasses all possible things that could happen, that means that the sum of probabilities has to add up to 1. The same normalization condition ends up being true of psi. So we have, from lecture 1, you'll remember that for a set of probabilities that sort of encompasses all possible things that could happen, the sum of p of x, or for a continuous function, the integral of p of x dx has to equal 1. And so the only new connection that we're making here between lecture 1 information and now lecture 2 information is that I just gave you a formula for the Born interpretation of the wave function and how p of x is related to the wave function. So now we have a condition that the integral of p of x dx is equal to psi squared dx is equal to 1. And we call this the normalization condition. And the logical grounding that I want us to have in place is that really this is just a statement, if I had to put it in words, to say the particle has to be somewhere. So the reason that I can integrate psi squared over all space and expect that to equal to 1 is really what I'm saying is, what's the probability, not just that the particle is at this x, but that the particle exists somewhere. And the good news about quantum mechanics is that we still obey the law of conservation of mass. Particles don't randomly appear in space and then disappear. They're always somewhere. We don't know where anymore, which is really unfortunate compared to classical mechanics, but we do know that it exists somewhere. And so because we know it exists somewhere, if I add up over all space the probabilities of where the particle could be, that will end up summing to 1. And so this is our normalization condition. And what I've put in the green box is frequently the most useful mathematical way of expressing that normalization condition when you get to your homework assignments. The second thing that we know about psi mathematically is it has to sort of look like a nice function. And to a mathematician, nice means the function should be continuous. Remember from your math class that a continuous function is one that doesn't have any gaps in it. And so a continuous function would look maybe something like this squiggle or something like this squiggle, but never like some sort of gap that shows up and disappears and goes somewhere else. So our wave functions look like nice continuous functions. They're also smooth, which in mathematical parlance means that we should expect their first derivatives to also be continuous. And they should be square integrable. Now, if you were a math major, you might stop me and say, wait a minute, we already said that it's normalized. By definition, it has to be square integrable, and I'll agree with that. I just want to point out that the definition of square integrable, which you might see in some of your textbooks as a prerequisite for this being an appropriate wave function, means that if I take the integral of psi over all space, that should come out to be a finite number. And so normalization is a stricter condition than that because it says not only should that integral equal a finite number, that finite number should be 1. But it's nice to point out that the wave function should be square integrable as a prerequisite. And then last but not least, wave functions are required to decay to 0 as we get very, very far away. That's probably not intuitive, but it's nonetheless true. And so I've written statement 3 in sort of mathematical formalism by saying the limit as x approaches either positive infinity or negative infinity of this function should go to 0. But another way of thinking about it is that typically our functions for the wave function look a lot more like this, where it's kind of decaying towards 0 as we get to bigger and bigger x values. And it does not look like this, where psi gets bigger as x gets bigger. All right, so that was fairly abstract. So let's go over an example of how we would think about these mathematical constraints in terms of an example wave function. Now, to avoid misconceptions, I should really point out that my wave function that I've magically handed down to us for this problem, it is not the wave function. This is not the wave function that describes electrons in hydrogen atoms and electrons in lithium atoms. It's just a mathematically reasonable wave function that you will see later in this course and on your homework sets, but that is situation specific. And so you don't know this yet, but this ends up being the appropriate wave function to describe a mass on a spring. Okay, so my magical wave function that I have gifted to us de novo, Deus ex machina style, that we're going to work with, I'm going to claim that it's a mathematically acceptable wave function. And to do that, I'm going to check that it's something that we can normalize, and I'm going to check that it looks mathematically nice. Now, whenever I encounter a function in quantum mechanics, I find it extremely useful to have the first thing that I do with that function be to visualize it. Wolfram Alpha is one of my favorite websites, and what's really nice is you can just type into Wolfram Alpha any function that you want, and it'll plot things for you. So here I've typed in e to the negative x squared. The a prefactor is Wolfram Alpha won't necessarily know what to do with a. Is it a constant? Is it a variable? So I find it useful to just plot the type of function and then know that a is a multiplicative scalar that's out in front. And so it'll make this function either bigger or smaller, but it won't change the shape of it. Okay, and so it appears that this function is kind of like a cone shape. This is actually called Gaussian function. And already we can see that this function looks to be obeying some of the nice mathematical properties that we were hoping for out of a wave function. You can notice that it decays to 0 as x gets bigger and bigger. It is continuous, so we don't see any sharp discontinuities or jagged lines. And you can't visually see it from this plot, but if we take the first derivative, you'll be able to notice that the first derivative is also a continuous function. So we're pretty good there. What I really want to focus on is the normalization condition. Is this a function that can be normalized? Is it already normalized? And how do we think about that? All right, so let's start this example of thinking about normalization of the wave function by writing down our definition of the normalization condition. That'll be a good place to start. So if this function can be normalized, then the integral of the wave function squared dx over all space should be equal to 1. And how I should start off is by first thinking about, well, what does it mean for this function to think about it over all space? And 2, what should my integrand be in this case? So over all space by default means negative infinity to positive infinity. Sometimes you'll learn from the problem that there's a different set of integration bounds that we should use to talk about what all space means. But if you don't see anything else in the problem statement, assume that all space means literally all possible values of x. So just to cover our bases, we're going to go negative infinity to positive infinity. And remember this psi squared notation. It's really only futzy if we're dealing with a function that has complex numbers. This one doesn't, and so what I'm going to do is take the complex conjugate of this function, which, because it's an entirely real function, didn't change anything about the function, and we'll multiply it by the original function. All right, so that's great for us so far, and I'm going to clean it up a little bit by, one, pulling out our constants outside of the integrand, and two, remembering some of the math that I learned in my pre-calculus course, which tells me that an exponential, when you multiply two exponentials together, that's the same as adding the exponents together. So this is equal to a squared times the integral from negative infinity to positive infinity of e to the negative 2x squared dx. Okay, so now we have to integrate this thing. And I don't know about you, but I don't immediately see how to integrate this. And the good news is, or the good news, bad news, is this isn't a function that's simple to integrate, but it is a function that is going to be really common in this course and where a table of common integrals helps you out. So the integral of a Gaussian is something that's well known in the literature. I did you all a favor of putting this on our Moodle page under our helpful reference data. So this is the table of common integrals that is in Atkins Appendix 1. And that integral table is either on your textbook or on Moodle for your reference. And if you look inside of this PDF, it has, as advertised, a whole bunch of useful common integrals. On the left-hand side, it has the indefinite form of these integrals, and on the right-hand side, it has the definite form. So if we scroll down a little bit, we'll see that our friend the Gaussian function is here and available. And the integral that we're given as just something that we're able to know is that the integral from 0 to infinity of e to the negative kx squared dx is equal to 1/2 pi divided by k to the 1/2 power. Okay, that's similar to what we're dealing with, so I'm going to go ahead and go back to our notes and write that down, but we'll have to unpack a little bit how to use this function. Okay, so we'll write this down as from our notes. So Appendix 1 tells us that the integral of a Gaussian of the form e to the negative kx squared dx is equal to 1/2 pi over k to the 1/2 power. And I'm going to double check myself just in case. Yep, I think I got that right. Okay, so comparing what I've written in green to what's in purple, we should be able to see that these are similar, like maybe we're on the right track, but we're going to have to do some algebraic manipulation first. And the reason that I'm spending some time going through all this math is that these are the common mathematical tips and tricks that we're going to need going on forward in the course. And so I want to have you see them in the context of a lecture first before you have to practice it on the homework. Okay, thing number one that we can do to try and make our set of our math that we're doing in purple look more like the math in green is to recognize that you can split up integrals and integration bounds just as much as you like. So the integral that we did from negative infinity to positive infinity, well, that's fine if we split that up into a component that goes from negative infinity to 0 and a component that goes from 0 to positive infinity. No problems. Our integrand is not going to change, just our limits of integration. And now we should be able to see that this second half of the integral really looks like our green integral. We'll have to do a substitution of clearly in this case k is equal to 2, but otherwise it seems like this integral has been solved for us. We're not going to have to do any work ourselves. The integral on the left the integrand looks right, but the limits of integration don't look good yet. So we're going to have to use one more mathematical trick in order to help us along in this case. And that mathematical trick is to notice something, which is that this integral is an even function. And from your math classes and your calculus class, hopefully you remember a set of rules about even functions and odd functions when it comes to integrals. So let me do a little brief aside. So an even function is by definition something where it's symmetric. It's a function where if you replaced all the x's with negative x's, the function doesn't change at all. So an example of this would be our x squared function that we had before. So here is the function x squared, and you'll notice that it's symmetric about this x equals 0 axis. And the really nice thing about thinking about integrals for these functions is that if you know what the integral is for an even function between negative infinity and 0, it's the same as whatever the integral is between 0 and infinity, because the area under the curve is the same. And so that implies for us that this even function is the same thing as the first half of our integral and the second half of our integral are the same. Again, that's because we're dealing with an even function in this case. How can I tell it's an even function? Well, if I substitute in negative x for e to the negative 2x squared, well, negative x squared just gives me back x squared, and so it's the same. It's an even function. What that means is that this whole expression is equal to 2 times the kind of right half of the function, the integral from 0 to infinity. And just like I alluded to earlier, if we substitute in for the appendix 1 integral, k is equal to 2, that means that we don't even actually have to do an integration. We can just plug in our result. So it's 2 times what appendix 1 told us this would be, which was pi over k to the 1/2 times a factor of 1/2. All right, before I move on, I'm going to give you kind of the second half of the aside, because it'll show up in a moment. What happens if we're trying to do an integral from negative infinity to infinity of an odd function? Well, an odd function is something where f of x is equal to negative f of negative x. So something, for instance, like x cubed would be an example of an odd function. My ability to draw cubes is okay, but not great. So hopefully you will just bear with me that I'm trying to draw a function that's symmetric about the x-axis, but flipped. And what's really nice about an odd function is that if we integrate over symmetric bounds, the two areas under the curve cancel out perfectly. And so for an odd function, if we happen to deal with it, this integral would just go to 0 if our function was an odd function. Okay, so hang on to that because it will come up later during today's lecture. All right, and now we're almost done with our math here. We just have one more idea that we have to note down, which is that I've done all this work to do an integral, but what does this have to do with normalization? Well, if we go back to the top of my math, what I've learned is that this function is normalized, but only for a very specific value of a. And so not just any a constant will do, but if we have some value such that 1 is equal to a squared times the 2 times 1/2 is gonna cancel out. A squared times pi over, oops, I should substitute in my k for equaling 2. Pi over 2 to the 1/2 power, then the function is normalized. And so let me go ahead and solve more explicitly for what a should equal in that case. So I'm going to get 2 over pi to the 1/2 is equal to a squared, and that means that our function is normalized if and only if a is equal to 2 over pi to the 1/4 power. And so it looks like, this wave function that I gave that was generic had a potential to be, or we've already used the word potential in class, has a possibility of being a good wave function. But we have to have a very specific value of a, and it's pretty common in quantum mechanics to have to solve for that value of a yourself, or to kind of complete the normalization condition yourself. So that's why I spent some time going over the math for this. Okay, and we already talked about this wave function, which I showed us visually. Again, it's really helpful to plot any new function that you encounter in this class using Wolfram Alpha or a program of your choosing. But we saw visually that the function was continuous, smooth, and it decays to 0. We could prove those things mathematically, and if you aren't convinced that it's continuous, smooth, and decays to 0, I encourage you to do some of that math yourself by checking that the function doesn't have any discontinuities, that you can take the limit of the function as x gets big and show that it decays to 0, and that you can take the first derivative and show that it's a continuous function. Okay, so let's take a step back now. We talked earlier about a mathematical interpretation of the wave function. It's a function, it has certain properties, but we still haven't really answered the chemistry question of what is the wave function. And I think it's honestly tough to give an answer to this. The Born interpretation may be the best physical handle we have on the wave function. The wave function by itself doesn't really tell us anything chemically, but the wave function squared, that contains a wealth of information because it tells us where an electron is likely to be. If your mind started thinking about GChem and orbitals and thinking about probabilities of where electrons might be, that's the right track to be on. The wave function is eventually what's going to tell us about the shape and the size of different orbitals that electrons can be in. But there's something new that we can learn from the wave function that is helpful to us as chemists that you didn't learn in your GChem class. And so in addition to this Born interpretation of a connection between the wave function and probabilities, we're also going to learn that the wave function acts sort of like an oracle. And by oracle, I mean that we can mathematically ask the wave function about some property of interest, and the wave function, as long as we do the correct math on it, will spit back to us not the value of that property, but the expectation value of that property. So because we're not in a classical world, I cannot ask where is the particle, but I can ask what is the average value of the particle, the average position of the particle, or again, because most of your textbooks are going to use the language of expectation values, what is the expected position of the particle? And I'm going to give you something called Aaronfest Theorem as an axiom. Aaronfest Theorem tells us that the expected value of some observable of interest, which normally those different observables depend on position and momentum. So the observable Q could be the position x, it could be momentum p, but it could also be what's the average kinetic energy of the particle, what's the average deviation of the particle from its mean. All of these things are possible values of Q, and Aaronfest Theorem takes care of all of them. And you'll remember, hopefully from our first lecture, that the reason we know on the left-hand side that we're talking about an expectation value is because these angle brackets showed up. And my letter Q is kind of an arbitrary choice, but it's my placeholder variable for whatever observable I want to talk about. Now, Aaronfest theorem tells us that that expectation value is related to the wave function. And so it's the integral over all positions x of the wave function times Q operator, which I'm going to get to in a second, times the wave function dx. Now, operators are probably new to you mathematically, and so we're going to do a brief tutorial about what are operators and what do they mean in a quantum mechanical world. Operators, notationally, we know something is an operator because we'll put a little hat over it, so that upwards caret, tells us we're dealing with an operator. And an operator is, like maybe you would expect based on the name, it is something. It is a function that modifies anything to the right of it. So this operator Q is going to act on the wave function. I'm going to give you some example operators to make this concrete, and I'll show you what effect they would have on the wave function. So in quantum mechanics, there are really only 4 independent quantities that we're going to have to focus on. So there are 4 basic operators that we're going to deal with. Some of them are boring, and some of them are a little bit more interesting. Our first operator is x. So here I've made a little chart of what the variable is classically. X is x, p is p, e is e, t is t. And then what the variable is quantum mechanically after the arrow. So our x operator is boring. It is x. So if I was using Aaronfest theorem to talk about my operator, I would just write out that the expectation value of x, where on the left, because I'm talking about a classical observable, I'm going to use the left-hand part of my little mapping table that I've given you. This is equal to the integral over all space of psi star x, because q hat is x hat in this case, and x hat is just x, again, because it's the most boring operator, psi dx. And you'll notice if I just move this x over in this case, no reason why I can't because x is boring, this looks exactly like the formula that we had for expectation values in our first lecture. The only substitution you have to do is you have to remember that psi squared is equal to p of x. And so we're right back at our formula that we had for expectation values in our first lecture. Not all operators are going to let us willy-nilly move the operator around throughout the integrand, and I'll show you how that in just a second. But for x, it's just multiplication like you're used to in your math class, and so there's no reason we can't move the operator around like we like to. A second operator that we are going to encounter is the p operator. The p operator is much more interesting. You'll notice that momentum, quantum mechanically, its operator is equal to negative I, that's just the complex number I, h bar, which is Planck's constant. The bar part means that it's Planck's constant divided by 2 pi. So we've got negative I h bar, and then d by dx. And so this is where an operator kind of gives a set of instructions, but not how to carry out the instructions. So our p operator, without talking about what function it operates on, we kind of just have to leave using this hanging notation. But if we wanted to substitute this into Aaronfest theorem, hopefully it'll become more clear what it means to think about the expectation value of p. So just like before, we're going to have psi star negative I h bar d by dx, because I'm substituting in on the right-hand side of my equation my operator psi dx. And here's our rule about operators. operators take whatever this operation is. In this case, for p, the operation is to take a derivative, and you're going to apply it to the function to the right of it. And so how I can simplify this or clean it up into mathematical language that'll look a little bit more familiar is that whatever psi star is, I am going to take the derivative of the wave function before I do my integral. And so what an operator is in quantum mechanics is sort of an opportunity, if you like, for us to apply a wave function to apply an operation to the wave function. And it's not probably obvious why the operator doesn't also act on the left-hand side, but that's just a convention thing. We have decided mathematical notation-wise that operators operate on the right-hand side, and they don't affect the left-hand side. All right, so we have two more operators that we're going to deal with in quantum mechanics. One of those operators is energy. Energy, kind of like momentum, also involves a derivative. So the energy operator is IH bar d by dt. And then we also have a time operator, which, like x, is very boring. The time operator is just time itself. Okay, so let's try and make this more concrete. Can we use Aaronfest Theorem and our newfound knowledge about a couple different operators that exist to determine the average position and, as a separate question, the average momentum of a particle whose wave function is the wave function that we talked about earlier in this lecture? And so our psi function, I'm going to, for most of this math, just leave our a constant as a because it'll look a little bit cleaner as we go through. But do make sure that we'll remember from time to time that a is equal to 2 over pi to the 1/4. Okay, so here we're going to try and determine the average position of the particle. And so the first thing that we should do is scroll back up one more time to Aaronfest Theorem and say, okay, our observable of interest is the position, so q is equal to x, and that means that q hat is equal to x hat, and we're going to surround q hat by the wave function. So we've got our integral over all space, psi star x hat psi dx. And now we'll do some substitutions. First thing I can substitute is, just like before, I know what my limits of integration are. Second thing I know is I know what my function is. Again, this complex conjugate stuff doesn't really matter here because we're not dealing with a complex function. I gave us a real function for simplicity of the example. And then we have e to the negative x squared. And so at this point, we don't see any derivatives that are sneaking around that might mess up whether or not we can move around different terms in our integrand. And so I am allowed at this point to go ahead and simplify this a little bit. I'm going to pull out my constants out of the expression. And I'm going to be left with x e to the negative 2x squared dx. And this now is an integral that I have to solve. So there might be a couple ways as a student that I would have gone about approaching this. I may have learned my lesson from the first time where it's like, okay, if I see a Gaussian or something where it's e to the something negative x squared, I should look in my common integral table, and I can do that here, but it doesn't give me, and I see an integral for x e to the negative kx squared dx from 0 to infinity, but I still will have to think a little bit about what the integral from negative infinity to 0 would be. But perhaps a better way would be to take a step back and before you do any integrals in this class, check if you can cheat. The way to cheat in this class is always special things happen if you're dealing either with an even function or an odd function. So let's go ahead and do a brief check. Is my integrand in this case special such that I can cheat and avoid doing any integration? So if my function that I'm dealing with, I'm checking if it's an even or an odd function, again, because those things make my life so much easier. If this is my function, that means that f of negative x is equal to, so I'm just going to put a negative sign anywhere I see an x, negative ex squared is equal to negative x e to the negative x squared. Aha! That is my same original function, but with a negative sign out in front. That means that I'm dealing with an odd function. And let's go ahead, just for fun, and use Wolfram alpha to verify that for ourselves. So now, instead of doing e to the negative x squared, let's go ahead and do x e to the x times negative x squared. Nope. All right. Wolfram alpha is clever, but not so clever that I can avoid putting in some parentheses. There we go. So if I plot this, this is another way for me to see that this integral is symmetric, but with a negative sign flip between x's a negative value and x where x is a positive value. And so since I'm taking an integral over symmetric bounds, the left half of the curve, which is all going to be, the area under it is all negative, is going to exactly cancel out with the right half of the curve, where the area is entirely positive. And so taking a few seconds to look at this was really helpful for us because we just avoided doing an integral. And if there's one thing that I love, it's avoiding doing integrals. So here is our function. We learned that the average position of this particle is 0. And I want us to note briefly that there's a special reason why this happened. The reason is that our function, our wave function, which remember is e to the negative x squared times a constant, that function, our probability tells us, what to expect about that function. Let's see if I gotta refresh my page real quick. Here we go. So just like, I want you to see this plot as operating in the same way that a histogram would, right? It tells us that the particle is most probable to be at the position x equals 0, and then it has kind of diminishing probability as x gets either very negative or very positive, but with equal probabilities. And so it's mathematically true that because this function is symmetric about x equals 0, that means that the average, when I add up all the different probabilities, because it's symmetric on both sides, or sort of equally weighted on both sides, that means that the average winds up exactly in the middle of this function. And so just by looking at this, I could have also looked at the wave function and said, based on interpreting this as a histogram, the wave function is going to have its average position around x equals 0. Okay, so that is our average position. And the last thing that I want to do is talk about the average momentum. So just like before, we're going to do an integral over all space of the complex conjugate of our wave function times p operator times the wave function dx. And let's go ahead and substitute in both our integration bounds as well as our values of the wave function. And so for this function, this operator, this derivative, is going to apply to this entire term right here. And so to simplify this expression, because we really need to like take care of all the derivatives that show up in our integral before we think about doing any integration, is we're going to need to take this derivative. And so when we take this derivative, the left side gets left alone, but this right-hand half evaluates to negative I h bar. My a can pull out in front, and then the derivative of e to the negative x squared is negative 2x. So my negative is going to cancel out with a negative to give me a positive. 2x e to the negative x squared dx. And when I simplify this and rearrange this, you should notice that this is going to look identical to, in terms of its functional form, to the integral that we did when we evaluated the expected value of x. In that what I'm left with in terms of my function is a bunch of constants and then x e to the negative x squared, or e to the negative 2x squared in this case, which means this is once again an odd function, and I can avoid doing the integral. And that means that this particle that's described by a particular wave function, its momentum is, on average, the particle is not moving anywhere, which means that sometimes it's moving to the right, but it has equal probability of moving to the left, and so the momentum cancels out to be 0, which kind of makes sense. There's nothing about this particle that says that it has a bias to heading right or heading leftwards. But the real reason that we know that its expected momentum is 0 is because we did the math, and we're going to trust the math on this one. Okay, and so where I want to end us off for today is talking about how Aaronfest Theorem leads us to the Schrodinger equation. And how Schrodinger came up with his famous equation is that he noticed that it's not just x, p, e, and t for which you can come up with operators. You can also do this for more complex functions. And so let's go back to our kinetic energy from the beginning of lecture and develop an operator for this kinetic energy. Well, if t is equal to p squared over 2m, that means that t hat is going to equal to p hat times p hat divided by 2m. And that means if I substitute in each of my operators, negative I h bar d by dx, second time negative I h bar d by dx divided by 2m, how this simplifies is, let's put together all of our constants. We're going to have negative I squared h bar squared over 2m. These two negatives cancel out to give me a positive, so I guess it's positive I h bar squared over 2m, but remember I squared is equal to a negative 1. So all of these constants are going to cancel out to negative h bar squared over 2m, and then derivative stack. So if I take a derivative and then I take a second derivative, it's the second derivative. And how we denote that is d squared dx squared. And so that is my kinetic energy operator. Now, v of x means that v hat is equal to, I'm going to substitute in x everywhere I see x. So v hat is just our normal potential that we were talking about before, which is why I can talk about a classical potential and a quantum mechanical potential, and nothing is really going to change. So I can talk about those in the same exact way that I would have talked about it in the classical mechanics course. So what Schrodinger did is he took advantage of the very famous idea that the total energy is equal to the potential energy plus the kinetic energy to come up with a governing equation for how quantum mechanics behaves. And so what he did was to say, well, if E is equal to T plus V, then in a quantum mechanical world, E is equal to T hat plus V hat. And substituting in the known operators that we have at this point of the course, so E is equal to I h bar d by dt. That is equal to what I just derived from my kinetic energy operator, negative h squared over 2m d squared dx squared plus v of x. And in this operator notation, I should say that the operator really only applies to terms that are immediately multiplied by it. So this operator is not going to apply to v of x. And again, is that intuitive? Not really, but it's what the mathematical notation suggests that we do. Now, if you are like me, it's typically confusing to see operators without seeing the wave function that they operate on. So when you see this equation in textbooks, typically you'll see it presented as multiplying both sides of the equation on the right by psi, so that not only can we see the operators, but we can see what they operate on. And if we do that, how this is going to change from our first equation down to our second equation is that I've just substituted in on the right-hand side in each individual spot psi. So the final time-dependent Schrodinger equation, which is one of the big governing equations we're going to use for this course, is I h bar d psi dt is equal to negative h bar squared over 2m times the second derivative of psi with respect to x plus the potential energy times psi. Now, frequently in chemistry, time doesn't really matter. We're talking about hydrogen atom, not necessarily in a dynamic sense, but just what's the ground state of hydrogen? Where are the electrons when hydrogen is not perturbed by an external force such that it's not changing its behavior as a function of time? And in that case, where our wave function adopts what's called a stationary state, and the time portion and the space portion of the wave function act independently. Now, in this little paragraph right here, there's an entire lecture packed in. And if you're really interested in the derivation for how I'm going to go from the time-dependent Schrodinger equation to the time-independent Schrodinger equation, I've posted an optional handout on Moodle so that you can look at that if you're the type of person who needs to see a derivation in order to accept a result. But for the rest of us, we're just going to accept as an axiom that this is what a stationary state is. And as we go through some of the lectures, we'll talk a little bit more about what it means chemically for something to be a stationary state. So in this case, for a stationary state, we don't really have to talk about the average value of the energy. A stationary state has a well-defined energy that's a constant. So we can say that the expectation value of the energy is equal to E, some well-defined constant. And Schrodinger's equation is going to simplify to the time-independent version, which is that E times psi of x is equal to negative h bar squared over 2m d squared psi x divided by, or second derivative of psi with respect to x, plus v of x times psi of x. And the only sneaky difference is that notationally, we'll start talking about lowercase psi, which only depends on x, rather than uppercase psi, which depends on both x and on t. Now, why would I introduce two of these equations, and which one are we actually going to use in our lecture courses going forward? I wanted to introduce, at least in passing to you, this time-dependent Schrodinger equation because some of you may be interested in a career that involves spectroscopy. And spectroscopy is all about a field where you take an atom and you use light to externally apply a force to that atom. Anytime you apply an external force, we're going to need to use the time-dependent Schrodinger equation. For this class, most of what we're going to focus on is situations of just what is the particle in its natural state? What does hydrogen do when we leave it alone? And in those situations, the time-independent Schrodinger equation is the primary one that we're going to use. So I'll try and help guide us on our homeworks a little bit where you should use which equation, but as a rule of thumb, if you're dealing with spectroscopy or external forces acting on a particle, you should use the time-dependent Schrodinger equation. And if I give you a homework problem where I give you capital Psi, which depends on both x and t, you should use the time-dependent Schrodinger equation. Otherwise, and what we're going to do for the majority of this course, is use the time-independent Schrodinger equation. Okay, so this last section, I anticipate, probably feels like a lot of abstract thoughts, and I'm going to leave us with that for today. Starting in Lecture 3, we're going to go through a case study which will hopefully not only make using the Schrodinger equation a little bit more comfortable, but will also answer a big question that you probably have in your mind right now, which is why? Why does the Schrodinger equation matter? Does it connect to some actual application of chemistry or something that we're interested in? And the answer to that question is absolutely yes, but it'll take us a lecture or two to be able to start to see those equations. So where I'm going to leave us today is with a summary. Quantum mechanics is a study of small systems. So when we start thinking about particles that are the size of an electron or maybe as big as a proton, we have to use quantum mechanics, wave functions, and the Schrodinger equation in order to describe the behavior of that particle. The wave function that describes the behavior of small particles like electrons and protons has to be normalized. And that means that it obeys sort of just a common sense idea of what probabilities mean. We should expect that the sum of all the probabilities over all space should add up to 1 because the particle has to be somewhere. And so it's really important that that wave function be normalized. It also should be continuous, smooth, and decay towards 0 as x gets really big. Assuming that we've solved for the wave function, which we have not done yet in this class, but will that be the subject for a couple lectures from now, the wave function has a physically meaningful interpretation because if we square it, we get that that corresponds to the probability that a particle exists at a certain point in time and space. And last but not least, the way that we can connect the wave function to some property of interest like the position or the momentum of a particle is using Aaronfest Theorem, which tells us that the expectation of value of an observable is equal to the integral of the complex conjugate of the wave function times the operator that corresponds to that observable times the wave function. And like I said, next time where we're going to go is to talk about the Schrodinger equation in both its time-dependent and time-independent forms and talk about how we can use that equation to solve for the wave function and then actually do some really interesting chemistry. So with that, I hope you all had a great time hanging out in our quantum world, and Team PChem, I will see you in lecture coming up soon. Take care, everybody.